Hello everyone, welcome to PCBE classes. Before starting the video, let me say you that this video is strictly for Btech first year students. I'll be covering one of the subject named Basic Electrical Engineering, which is required for all the freshman engineering students. So let's get started. Today we'll be discussing one of the topic of basic electrical engineering named as DC machines. Now, what is a machine? Machine is basically something that reduces the human effort. Human effort means physical effort or mechanical effort. We can take some of the examples like fan, washing machines, grinder, water pumps, motors, generators, and so on are the examples which says that energy conversion devices are said to be the machines, and which involves electricity are said to be the electrical machines. These electrical machines are of two types depending on the type of supply. If it is a DC supply, it will be DC machine. If it is AC supply, then it will be the AC machines. And depending on the type of application, it's again classified into two types. One is generator, which converts a mechanical energy to electrical energy, and second one is a motor, which converts electrical to the mechanical. Now moving to the next slide. Now this conversion of mechanical to the electrical or vice versa can be done only with the help of a magnetic domain. So, in order to understand the concept of working of machines, one should know certain principles and rules. So, let us move to the first principle, Faradays electromagnetic induction law. What it states? It states that when the magnetic flux linking a conductor changes, an EMF is induced in the conductor, which means the EMF can be induced only if there is a rate of change of flux linked to the conductor. That is, EMF is proportional to the d phi by dt. But here the EMF induced can be in two ways. That is, when conductor moves within the magnetic field, then due to the rate of change of flux linkage, the EMF is induced in the conductor. Or when the current flowing in a conductor is alternating in nature, thus the flux produced is also alternating in nature, hence the EMF induced in conductor. These ways are classified as the two laws of the Faraday's electromagnetic induction law, which is, in the first law it is statically induced EMF, and in the second law it is dynamically induced EMF. We can take certain examples. For the statically induced EMF, the example is the transformer, and for the dynamically induced EMF, the examples are the machines, that is DC or AC machines, that is otherwise known as generator, and the motor. Moving to the first law of Faraday's electromagnetic induction law. Here what happens, the conductor is stationary and the magnetic field is moving or changing. So the EMF induced is called statically induced EMF, as the EMF induced in conductor is stationary in nature. What does the second law says? Here the conductor is moving in a stationary magnetic field in such a way that the flux linking to it changes its magnitude. So the EMF is called dynamically induced EMF, as the EMF induced in conductor is in motion. In the previous slide, we have gone through both the laws of Faraday's electromagnetic induction. There we have studied about the first law and the second law. The first law is statically induced EMF, which belongs to the topic transformer. Thus, we will be discussing the transformer topic later, so we will be focusing on the dynamically induced EMF. As we are covering machinery part, so let us focus on dynamically induced EMF. From the previous slide, we can conclude certain requirements for the EMF generation. That is, the first thing, we have to attain the change in magnetic field or flux, otherwise known as magnetic lines of force. But from where we will be getting this magnetic flux? Obviously from a magnet or a magnetic material. And then within this magnetic field, if a conductor rotates, then rate of change of flux will be linked to have induced EMF in conductor. So let us have some brief idea about magnets. Magnets are of two types. One is permanent, another is electromagnets. Permanent magnets are naturally found magnets and having weak magnetic field with aging effect. Aging effect means in long run its magnetic effect decreases. But electromagnets are the artificial magnets which are made from ferromagnetic material, which is wound with copper coil, and when current passes through it, it becomes magnet or acquires a magnetic property. That means its magnetic effect depends on current magnitude and can be altered by altering magnitude of the current passing through the coil. This implies that its magnetic field is strong or can be more stronger depending on the supply, and hence there is no aging effect. So which magnet is preferred? Definitely the electromagnet will be preferred. Now let us know how we make the electromagnets. Electromagnets can be made of two types. For making electromagnet, first we require a ferromagnetic material or an iron core. Over that we have to own some copper windings or copper wire. If to this copper winding, if we give supply, let us give DC supply, then it produces constant magnetic field. If we give to AC supply, then the flux which will be produced will be alternating in nature. Let us move to the next slide. From the previous slide, we knew that how the flux is produced from magnets. Now let us assume the flux are traveling from left to right. As you can see, the blue dotted lines indicates the flux is traveling from left to right. And then if within them I keep a stationary conductor, that is a red line indicates a stationary conductor. Now what's the status? Now here the flux is traveling from left to right, that means the flux is present. But is there any rate of change of flux? That means, is there any flux linking to the conductor? No, definitely it is no. That means there is no opposition to the flux, which indicates rate of change of flux is equals to 0. That is mathematically can be said as d phi by dt is equals to 0. If the d phi by dt is equals to 0, then the EMF induced to the conductor is 0. Now suppose the conductor starts rotating, like you can see from the slides. Here the conductor now starts rotating. At every moment or every angular moment, you can see that it cuts the flux. That means what happens? there is rate of change of flux is linked to the conductor. That means when it cuts the magnetic lines of force, an EMF is induced in the conductor. Right? So we can say that here the conductor cuts the flux, and thus the rate of change of flux linked to the conductor, an EMF is induced in the conductor. What is the conclusion we have drawn? We have drawn certain conclusion that for generation of electrical power or energy, we need to rotate a conductor within a magnetic field. And in order to have magnetic field, we should have certain magnets. So conductor is placed within the magnets or between the magnets. Here we use the electromagnets, and for this we use copper winding over an iron core for production of the magnetic field. And these windings are said to be the field winding supplied by a constant supply for production of constant or stationary flux or magnetic field. This is what about the lecture 1. In the upcoming videos, that is a lecture 2, we will be dealing the other things of the DC machine. Thank you.